Hello everyone, I'm Haoyu from Indiana University. This work is written by me and my advisor Zhang, which also from Indiana University. And we studied the edit similarity join problem. So let's see what is the edit distance. So consider two strings, x and y. The minimum number of operations, including insertion, deletion, and substitution required to transfer string x into string y is their edit distance. So let's consider the following example. We have two strings. In order to transfer the first one to the second one, we need to do a substitution and a deletion and again substitution. Thus, the number of edits is equal to 3, which is also the edit distance between them. So the edit similarity join is given a collection of strings and an edit threshold k. Report all pairs of strings with edit distance less than or equal to k. So consider we have a database with 4 strings, S1 to S4. And here is the pairwise distance between them. Given a threshold 3, we need to report S1, S2, and S1, S3 because their edit distance is smaller than 3. So this problem is really important in the following applications in data cleaning, integration, bioinformatics, collaborative filtering, and natural language processing. And the edit similarity join has been identified as a primitive operator in database system. So here are the following existing approach. So this problem has been studied extensively. According to the survey, those 4 methods are the most efficient one, and all of them are based on a filter and verify framework, which for each string, it computes a signature based on qgram or partition. And 2 strings share a common signature are identified as candidate pairs, and it verifies all the candidate pairs via edit distance algorithm. However, we observed that the performance of all exact algorithms degrade when the edit threshold is large and the input strings are long. So according to a survey, an error rate of 20% and 25% pushed this technique to the limit. So by saying 20% error rate, so we are talking about the edit threshold k is 20% of the string length. However, in some applications, long strings and large threshold is critical. For instance, the total length of human genome is over 3 billion base pairs. So on genome data, if the threshold is too small, you may end up with 0 output pairs, which is certainly not interesting. So here is the outline of this talk. At first, we will introduce the idea of EmbedJoin and the tools we used in our algorithm as building blocks. And then we will talk about the algorithm and experimental result. At last, we make a conclusion. So the idea of EmbedJoin is to solve edit similarity join problem via hashing. So let's consider. We have several strings, and we want to compute some random hash functions to compute multiple such kind of functions. So the function should have the property that the collision probability is high when the edit distance is small, and the collision probability is low when the edit distance is large. So this kind of hash function is also called locality sensitive hashing. And we want to build multiple such kind of hash tables, and we expect the similar pairs will be hashed into a same bucket in at least one hash table. However, the problem is there is no LSH function for edit distance. In order to solve it, we decide to first embed all the strings from edit space to Hamming space. Here, I'm saying the term embedding is very different from the embed of all the presentation in this section. So this embed is metric embed. It's not network embed or topic embed. So it's a different term. And after embed to Hamming distance, we use the LSH in Hamming distance. So during the embedding, we want the pairs with small edit distance will also have small Hamming distance after the embedding, and pairs with large added distance will have large Hamming distance after the embedding. So in order to further define the quality of embedding, we define a distortion, which is the Hamming distance after the embedding divided by added distance before embedding. So we want the distortion to be small. And next, I will introduce the tools we use in embedding and hashing. So the tools we use in the embedding is called CGK embedding, which is named after the three authors' last name. So you can think about it as a embed function f, which embed a string with n character to 3n character. And the algorithm needs some random hash tables, 3n random hash tables. Each of them hash every letter in the dictionary to a random number 0 or 1. So here is an example for the first hash table. So consider the dictionary is genome data. So we have 4 letters, A, C, G, T. And every letter in the hash table is a random number from 0 or 1. So let's see an example. If we have the following input, the algorithm keeps a pointer, which is initially set to the first digit of the input. In each step of embedding, we first copy the letter from the pointer position, which is A in the first step, and then we increment the pointer by the hash value, which is 0 on the first step. Thus, and we come to the second step, we also copy the letter from the pointer position, which is also A, and we have a new hash table. And we find the hash value is 1. Thus, we increment the pointer by 1. In the third step, we copy C, and we increment the pointer by 1. And in the fourth step, we copy T and increment the pointer by 0. We keep doing this until the output have 3n digits. And an issue is, if the pointer reaches the last bit of the input, we just append an arbitrary character outside the dictionary, outside ACGT, a random one. So let's see what CGK embedding gives us in theory. If the added distance between a pair x and y is less than k, the distortion could be bounded by OK, which means with high probability, the Hamming distance after embedding is greater than added distance, less than or equal to added distance square. And the distortion could be further decreased if you use multiple embeddings. So here is a plot shows the CDF of 1,000 random pairs and a different number of CGK embeddings. So x-axis is the distortion, y-axis is the percentage. We change the number of embedding from 1 to 9. As we can see, after increase the number of embedding, the minimum distortion decreased a lot. So the second tool is called locality sensitive hashing. So the locality sensitive hashing for Hamming space is for vector space with n character is just choose random bit from the whole vector. So it's very simple. So consider we have the following 2 strings, and one LSH function is just one random bit from the whole vector. So under this case, they are not matched. In order to amplify the gap between similar and dissimilar pairs, we use a standard AND/OR amplification technique, so which is by selecting m such kind of hash table, hash functions, and each of them are randomly sampled from the hash family. So in this case, we choose these 3 positions. The signature of the first string is BAA. For the second string is AAB, so they are not matched under this hash function. And we can choose multiple such kind of hash functions. So in this case, they share a signature BBB. So we choose these such kind of hash functions, and 2 strings are considered to be matched if they share at least one signature under a hash function. So we will find some candidate pairs after the locality sensitive hashing, and then we do a verification via the exact added distance algorithm. So here are 3 algorithms. So the traditional dynamic programming ones use time complexity n squares, and the Euclidean algorithm use ONK, time complexity. So n is the length of the input strings. So with surface tree, it could be boosted to n plus k squares. However, surface tree is computationally expensive to build in practice. Thus, we just use the Yoconian algorithm to verify. So here is a whole picture of our algorithm. For a collection of strings, we first embed them from edit space to Hamming space via CGK embedding. And then we perform LSH on Hamming space. So here M is equal to 2. Thus, the length of the signature is 2. And Z is equal to 2. We use 2 hash tables. So in the first hash table, string 1 and 2 share a signature AT. And in the second hash table, string 1, 2, 3 share a signature AC. Thus, we have candidates S1, S2, S1, S3, S2, S3. And we repeat the process for R times by embedding multiple times and repeat above procedure to get more candidates. At last, we do an exact verification using edit distance algorithm, and we output all the pairs with edit distance less than or equal to k. So here are parameters in our algorithm, so which is R, number of embeddings, Z, number of hash functions, and M, number of the length of LSH signature. The choice of these parameters depend on datasets, threshold, time, space budget, and accuracy requirement. So for instance, when you increase the R and Z, you could decrease the number of false positive. However, you will also increase the number of false positive. So by increasing the number M, so two signatures are harder to match. Thus, you will increase the number of false negative. So from our data set we test, these parameters works good. So in order to further speed up, so consider the Hamming LSH requires strings with same length. However, in real-world data sets, the strings are in different lengths. So for instance, this is a string length distribution. The X is the length of string and Y is the count of strings. So a naive way to solve this is just to embed all the strings to 3 times n max, which is the maximum length of all the strings in the data set. And the following two strategies could speed up the naive way because the n max could be really, really big. So we can grouping partition strings with similar lengths into groups, or truncate each embedded string of set 3n max to 3n average. N average is the average length of strings in our data set. So as we can see, most of the strings are almost in the same length. Thus, the truncation method works good in our experiment. So here comes to our experimental results. We have 4 comparisons: pass join, Q trunk, dep join, and ed join. And we make the following measurements, which is running time, memory usage. And for our algorithm, since our algorithm is an approximation algorithm, we also report the accuracy. And note that our algorithm, due to we use an exact verification process, we will only have false negative. Thus, the accuracy is just the number of output divided by number of ground truths. So here's the data sets we use. We use UniRef, track, and genome dataset with average length, small, medium, and large. And for genome dataset, we change n, which is number of strings, from 20,000 to 320,000. And we change the average length from 5,000 to 20,000. So here is only for our algorithm, the running time on different parts of EmbedJoin algorithm. So we measure 3 parts. The first part is read and embedding. And the second part is compute the LSH signature, hashing, and find candidates. And the third part is the verification. As we can see, when the string lengths are small, so in the first 2 data sets, the first 2 parts almost dominate everything, the whole running time. And when the string length is large and the threshold is large, So verification time dominates the others. So here is the running time comparisons varying k, which is the edit distance threshold. And as we can see, the dark blue line is our algorithm. We always have the best time comparison, time performance on this data set. And the number here are the accuracy. We always guarantee our accuracy is greater than 95% on UniRef and track dataset, and greater than 99% on genome dataset. And so we have the following speed up at the largest k value in each dataset, with 5.2 times speed up, 12.1 times speed up, and 6.2 times speed up. And in our comparisons, when threshold is small, the path join, which is the black one, have the good performance. And when the threshold is large, the green line, which is Q trunk, have good time performance. So here is the running time comparisons varying n, which is number of strings. And I think all the performance of all algorithms are similar. So they are following a similar trend, and our algorithm always have the best time performance. So here is the memory unit usage comparisons varying k. So k is also is the threshold, and y-axis is the memory usage. And our algorithm use the smallest memory. And I think all algorithms have similar memory usage performance, except the path join. As you can see, the dark black line. So the memory increased rapidly with threshold k. So here is the scalability on string length. So we change the string length from 5,000 characters to 20,000 characters, and we change the threshold from 1% of the string length to 20% of string length. So the y-axis are time. So as we can see, our algorithm always outperforms others' algorithm, and only when the threshold is large, only our algorithm could finish. And in the largest data set, only path join produced 1 point, and we can finish all of them. So some points are missing here because of implementation limitations, or programs cannot finish in 24 hours. Since we get all the programs from the author's web page, so there are some limitations, including reporting error outputs or memory leak. So the next one is the scalability on number of strings. We change the number of strings from 20,000 strings to 320,000 strings. And also we change the threshold from 1% to 20% of the string length. And I think the result is similar. Our algorithm obviously output the others. And in the last data set, only our algorithm have point. So I want to make a conclusion. So the EmbedJoin algorithm outperforms all the previous algorithms in both running time and memory usage on long strings and large thresholds. And our accuracy is high, so which is more than 95% on small data set and 99% on long data sets. And it scales very well up to high error rate on large data set, which is beyond the reach of all the existing algorithms. Thank you.